Most LLM streaming bugs start before the first token, at the transport choice. I'll show when FastAPI should use SSE, when WebSockets are justified, and what each one brings. This is the workflow you'll know how to run when we're done, which evaluates request needs and decides the best streaming transport. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Streaming an LLM response looks simple. A model emits text over time, and the user sees it as it appears. The pain is not the model. It is the transport or. Pick the wrong one and you get head-of-line blocking, wasted compute, or stale control. Success here is smooth first token latency, cheap one-way delivery when you only need output, and fast bidirectional control when the user may stop or adjust generation. Think of SSE as a water tap. You open it and water flows one way. Think of WebSocket as a walkie-talkie, two-way control, back and forth. For many chat situations, the tap is cheaper and simpler. For interactive sessions where the client must tell the server to stop or change parameters, the walkie-talkie is necessary. We will build a small set of FastAPI examples you can run in tests. Each example mimics a tiny LLM stream and shows a concrete trade-off. The code uses a TestClient to exercise the server so you can see timing, cancellation, and throughput without a browser. Now, let us get to the first concrete example. This snippet streams tiny tokens over server-sent events using FastAPI and verifies delivery with TestClient. The FastAPI app defines an SSE route that returns a streaming response, which yields lines in text event stream format from the inner generator gen. The generator emits two data, lines with a small sleep to mimic token-by-token output, similar to an LLM stream. Using TestClient.stream, the code opens a streaming get and iterates lines with decode Unicode enabled, so values are readable text. All lines are collected into the list longs for a concise check. Increasing the sleep increases perceived spacing between tokens. The print confirms the event count and the final event value, proving basic SSE flow. Next, we will contrast that with a simple WebSocket that times first token latency. This code opens a FastAPI WebSocket and measures time to the first token received. The WebSocket route, WS, accepts the connection, sends two small text messages with a short asyncio sleep between them, then closes. On the client side, TestClient.WebSocketConnect performs the WebSocket handshake and returns a context whose receveText method pulls messages. The variable T0 captures the moment just before connecting, and DT computes the time until the first message arrives. The short sleep controls pacing. Increasing it will raise first message latency, while decreasing it reduces head-of-line delay. The print highlights the observed first token latency and message, illustrating basic WebSocket streaming. Now, we will learn how SSE behaves when the client cancels midstream. This example shows how a client can cancel an SSE stream mid-flight to save time and tokens. The SSE long endpoint returns a streaming response that yields 10 data events with a small delay to mimic incremental generation. On the client, TestClient.stream opens the stream, and the for loop enumerates lines as they arrive. The conditional break at the third event simulates a user stop, closing the context and signaling the server to stop sending. The variable n records how many events the client chose to read. Reducing the break threshold aborts even earlier, reducing compute and egress. The print confirms early cancellation occurred after 3 events, demonstrating SSE cancel behavior. Next, we will show how a WebSocket allows cooperative cancellation initiated by the client. This snippet demonstrates cooperative cancellation over a FastAPI WebSocket by sending a stop command. The /WSGen route accepts the socket and starts a background task using asyncio create task to await an inbound message. While streaming tokens with send text, the loop periodically checks if the stop task has completed and whether the received message equals stop. If so, it breaks early and closes the socket. The client reads 2 tokens, then sends stop to request termination. Lowering the number of initially received tokens cancels sooner, reducing wasted work. The print shows exactly how many tokens arrived before cancellation, proving bidirectional control with WebSockets. Now, we will wrap the decision process into a small benchmark and a chooser. This code makes a simple decision and benchmarks the chosen FastAPI pattern. The variable needs_BiDi flags whether your app requires bidirectional control, and end-clients hints at concurrency. Together, they select WS or SSE. For SSE, it streams all events from SSE long using TestClient.stream and counts tokens. For WebSockets, it receives a known number of tokens from /WSGen using WebSocket Connect. The code then measures elapsed time and computes tokens per second for a quick throughput check. If you increase end clients or require cooperative stops, WebSockets tend to be favored. Otherwise, SSE is leaner. The print names the chosen transport and its throughput, grounding the decision. In a real project, UMap needs BiDi to user actions. If users only read output and never send mid-generation edits, SSE wins for simplicity and lower overhead. If users can press stop, rewind, or change temperature during generation, choose WebSockets so you get immediate control and fewer wasted tokens. Recap: SSE is one-way streaming, simple and efficient for read-only flows. Use WebSockets when you need bidirectional control or cooperative cancellation. One caveat: WebSockets add complexity and state, which can complicate scaling. Next step, run the benchmark with more concurrent clients and compare tokens per second as you increase concurrency and cooperative stop events. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.